In this video, we're going to explore the concept of power set of a set. Consider a set A, or maybe rather a set X. A set has elements. Let's suppose that the elements of the set X are A, B. I'm going to switch to small letters for the elements of X because I'm going to use later on the capital letters for something else. So let's say X has three elements, A, B, and C. Then it is going to have a number of subsets. In fact, let's make a list of all possible subsets of X with three elements A, B, C. We're assuming that all three elements displayed here are different sets from each other. So the empty set is a subset of X. It is a subset of any set, right? So in particular, it will be a subset of this X we've got here. Well, how are the subsets formed? We need to take a grouping of elements of X, and then by restricted comprehension, we know that it's going to be a subset. So the smallest grouping is the grouping of no elements, that's the empty set. And then we have a grouping of a single element, and there are three such. The set whose element is A, the set whose element is B, and the set whose element is C. And then we have groupings that have two elements, AB, BC, and AC. And finally, we've got the entire set X, the grouping of all elements of X, A, B, C. So in total, we have 1, 2, 3, 4, 5, 6, 7, 8. The number at this point is irrelevant. What we want to do instead is to consider a set whose elements are going to be all possible groupings that we've formed. So in our display notation, if the empty set is represented by this dot, and also the same for the other sets, if these dots represent those sets, then the set formed from this collection of all of these sets is going to be called the power set of X and is going to be denoted by P of X. So this reads as power set of X. In other words, the power set of a set is a set whose elements are all possible subsets of the given set. We can write this out in set theoretic notation as P of X being equal to the set of all possible S's, and that's where I use the capital letter, such that S is a subset of X. Just a side remark, the notation is irrelevant. I could have used a small letter here for S as well, and I could have used the capital letters for the elements of X as well. It's just for more clarity, it's sometimes convenient to distinguish sets and their elements by using capital or small letters, but in fact all elements of sets are sets themselves. So this is rather a local distinction that is relevant for a local discussion, and in general there is no distinction between sets and elements because all elements themselves are sets. And keep in mind also that the element is a binary relationship, so it's like the notion of a friend. It doesn't make sense to talk about friends in general, it only makes sense to talk about a friend of a particular person. So in a similar way, there is no meaning in element in general. without referring to a set of which you're taking an element. So in this case, A, B, C are not just elements just like that, they are elements of X. So that of part is important, and without the of part, the notion of element doesn't make sense. So coming back from this detour, the power set of X can be represented in the set theoretic notation like this, which reads that it's the set of all possible S's such that S is a subset of X. So in other words, it's a set of all possible subsets of X. Now, how do we know that the collection of all possible subsets of X, like this one here for instance, is going to form a set? In fact, we don't know that without introducing this as an axiom. And this leads us to the power set axiom, which says that for any set X, the collection of all subsets of X, in other words, the collection of all S's that are subsets of X, forms a set. So that's the power set axiom. And then the set formed by this collection is called the power set of the given set and is denoted by P of X. Now, coming back to the question of the number of elements of the power set, in other words, the number of all possible subsets of a set, we dismiss that question because that question is not really relevant to the definition of the power set, but it still might be interesting to see how many subsets a given set could have. In the case when we had a set X with 3 elements, the power set, as we counted them, turned out to have 8 elements. So for 3 we get 8. It would be interesting to explore what other numbers do we get by changing the number of elements of the initial set, and then to see if there is any pattern that emerges from this table, from a table like this, and then to maybe come up with a rule for this pattern, and finally to show by mathematical proof that the rule is actually valid for all sets X. I leave this for your own exploration and fun, although it is likely that if you're watching this video you already know what the answer is. Even if you do that, perhaps you don't know how to confirm the validity of that answer, and this could be a question you could think about. Thank you.